Hi, Year 10. I hope you've had a good weekend. Just before we start going through this, I just wanted to mention that there are a couple of you that seem to be struggling to keep up with the work. And if you do, please do let me know, and I can just tell you the particular questions that may be most useful, or just talk through things with you on Show My Homework, the messages on Show My Homework, just to make sure that we both know which lessons are really crucial and just so I can keep in touch with you really. But the vast majority of you just seem to be doing the work as soon as I set it. It comes straight back to me within a couple of hours. I'm so impressed by how a lot of you seem to be managing your time, but I'm really aware that you're all doing different options, so it's going to be different for all of you. So some of you, I'm sure, are doing other options that are setting a lot of work, and that probably is making it more difficult for you. But please just keep in touch and let me know, because after half term I'm intending to start going through new stuff. So if I know where you are, then at least I can make sure that I tell you the bits that are going to be most important for you to do. Okay, let's quickly go through the answers to these ones then, shall we? So first question about group 7, and this isn't to do with the rate calculations, those equilibrium questions. There are a couple of questions, like I said, that aren't. But it's always useful to keep ourselves up with this sort of thing anyway, isn't it? So products form when chlorine solution reacts with potassium iodide, and they've told me chlorine's more reactive than iodine, so I don't even need to remind myself of that reactivity. Although I should know that from the reactivity change going down group 7, but anyway, they've told me that anyway. So therefore it's a displacement reaction, and it will happen because the chlorine's more reactive. It will displace the iodine. So I will make potassium chloride and iodine. Or obviously I could accept KCl and I2. Be careful there though if you use the symbols, that iodine's one of the ones on the hockey stick. It's one that goes around in pairs, isn't it? Why is chlorine more reactive than iodine? Well, we always need to say the same things, don't we? We need to mention distance, shielding, and whether it gains or loses. And in this case, it gains, doesn't it? So therefore, the outer electron, I'm going to say why chlorine is more reactive than iodine. So the outer electron is closer to the nucleus, or I could have just said it's smaller or there are fewer shells. Shielding, so therefore there's less shielding, or equally I could have said the greater attraction to the nucleus. Would have got me that mark as well. And then I'm going to mention the fact that that makes it easier to gain electrons. Or I could have gone through that whole process but said the opposite, because I could have said in iodine the outer electron is further from the nucleus. So I could have just done it the opposite, couldn't I? Chlorine reacts with hydrogen to form hydrogen chloride. Why is hydrogen chloride a gas at room temperature in terms of structure and bonding? So hydrogen chloride is a simple covalent molecule. It's one of the ones I have to know. So if it's a simple covalent molecule, I know straight away that why is it a gas? It has weak intermolecular forces, which therefore need little energy to overcome them. That's a nice simple 3-mark one that we should be used to from our structure and bonding topic, just to remind ourselves of it. So this is the first calculation, and it's not an easy one. So it's not as easy as the ones that were on the video, and I put a couple of these in just because I think it would challenge you. I'm sorry if it's challenged you a bit too much, hopefully not. And I just think it's useful to see something a bit different so that we know the sorts of questions that could come up. So they've given me the formulae as the display formulae there quite nicely. First thing I always do is I always put my plus and minus just to remind myself whether the reaction gains or loses energy on each side. So on this side, energy is going to go in, it's going to gain energy. On this side, energy is going to come out, it's going to lose energy. So therefore, I know which sign to use on each side of the equation. I saw a lot of you laying these out beautifully in your work, so that's great. So I've got 4 CH's, I've got 4 times, and this is the plus side, 4 times 412, added to 1BR, 193. So on that side I've got plus 1841. I'll actually go on to the next line down for the other side. So on the other side I've got, and what it's asked me to find is the bond energy for the CBr bond. So it's this bond here that I'm trying to find out the energy for. So therefore I've got 3 now of the CH bond. So I've got 3 412s this time. I've got a HBr, so I've got 366. And then I've got my unknown bond, the CBr bond, which they've called X there. And this part here, if I add all those together, is 1602 plus X is some unknown number on the other side of the equation. I don't know what that is because I don't know X yet. So therefore, if I know, and sorry, that's minus, isn't it? Because all of these are minus on this side. So therefore, if I know that the difference between these two numbers, so therefore 1841 take away minus 1602 plus X is equal to minus 51, then I can work out that X must be 290. And I don't need to put a plus or minus sign next to that because it's a bond energy that we found out, not the energy in this particular case when the bond was made. They're asking you to calculate the bond energy here, but you wouldn't have marks taken off if you did use a sign for that. Okay, next question. I've got my reaction between ethene and bromine. It's given me the equation, reaction profile here, and it's given me where the reactant started out and where the products ended up. It's asked me to complete the reaction profile. So the first thing it's looking for is that I've included an activation energy that I've got on, up and then down. That's only 1 mark. And it's also asked me then to label the energy given out, which is the difference between the reactants and the product. So that's the energy given out, or delta H, and then the activation energy, which is this energy here. That's the activation energy. So that would be the other 2 marks. When ethene reacts with bromine, energy is required to break the bonds. How does a covalent bond hold atoms together? So we know that in a covalent bond, what happens is we have shared electrons here, which it's then what is holding the bond together is actually, these are opposite charges, so it's actually the electrostatic force of attraction, of course, and that is between the shared pair of electrons and the nuclei of the atoms. Okay, and then we have another calculation. So I've got my display formula given again, and this time I'm looking for the BR bond is the one that I'm trying to find out about. So I have my bonds broken and my bonds made, so I have my pluses and my minus, and then I will work through the calculation. So first of all, I have my 4 times CH bonds, which I can times by 4. I then have my C double bond here, and that, to be honest, is always the one that people forget of the carbon-carbon bonds. So don't forget those carbon-carbon bonds. I've got my carbon-carbon double bond there, and then I have my X, the one that I don't know. So I can calculate all of that and find out it's 260 plus X will be how much energy is taken in when the bonds are broken. I then need to find out on the other side how much energy is released when all these bonds are made. So I've got 1, 2, 3, 4 CH bonds. So therefore I've got 4 times 412 on this side. I've got 2 CBr bonds. So I've got 2 times 276. Oh, I keep forgetting to put my minuses in, don't I? You're much better at this than me. I noticed looking for your work. And then I mustn't forget my carbon-carbon bond. It's the one that I always forget. And so I've got minus, because energy goes in, comes out, sorry, when that bond is made. So there we go. So if I calculate all of that on that side, I end up with minus 2548. Oh, I know that. 2260 plus X on this side. Take away 2548 on this side must be equal to the total energy changed for the reaction, which is minus 95. So therefore X must equal 193. Okay, quick equation to balance. So yeah, I won't run through it actually. I just think I'm just going to stick the numbers on. So sure, 2 there and 2 there, because I think that it's the sort of thing that we can go through in class if people still need more practice of it. We'll do more practice of that in class. So alcohol used as fuels. It's a funny question, this, isn't it? Because it's basically physics. This is an equation that we use in physics, but they give the equations. We can just stick the numbers in, can't we? So we're calculating the heat energy in joules. The tricky thing about this is understanding this practical and what's going on. So this is what I always say to you, is stop and look at what they've given me and really think about what's happening here. So I'm using some alcohol to heat some water, and it's investigating the energy released when the alcohol burns, and the temperature of the water has gone from 22 to 38.4. The mass of alcohol burned was 0.8. There's 50 grams of water. So I've been given 2 different masses. Which is the mass that I'm interested in? Well, it's the water that's changing temperature. It's the water that I'm being given the specific heat capacity for. So therefore, it's the water that I'm interested in, what mass of water I've got. How much alcohol's burned is completely irrelevant here. So it's really important, like I say, to really stop and think about these sorts of things. It's so easy just to see the first mass, which here, they've been a bit naughty really, because they've put that out on its own there, so you'd pick that one up really quickly, rather than noticing in the text they've given you the mass of water if you hadn't stopped and thought through it. So therefore it's 50 grams. Now, do I need to turn that into kilograms? No, because they've used grams here. So therefore I'm using grams as my unit of mass. So 50 grams times 4.2 times my temperature change. The difference between that and that is 16.4. So I already have got 2 marks there. I've got a mark for working out which mass to use, and I've got a mark for working out the temperature change. And then I just need to finally do my calculation, which is 3444 joules. And the real reason that I chose this question, of course, is the next bit here, which is the calculation, the bond energy calculation. And this is a nice simple one. This is much more like you're used to. And so I'll put this a bit later on so that you can start feeling like you know what you're doing, hopefully, at this point. So I'm going to do my minus before I start. So my pluses. So all of these are energy gains. So what have I got? 1, 2, 3, 4, 5 CH bonds. I've got 1 CC bond, which is the one I always forget if I'm not careful. I've got a CO bond, and I have got an OH bond, and I've got 3 OO double bonds. Okay. So if I add all that together, I get 4722. If I then do negatives, so I have got 2 of this, so each has got 2, so I've got 4 C double bond O's. So where's C double bond O? Here it is. I have got 3 of these, so I've got 6 OH's, so 6, 7, draw together makes 5, 9, 9, 8. So therefore, 4, 7, 2, 2, take away 5, 9, 9, 8 is minus 1, 2, 7, 6. The reaction is exothermic. Explain why in terms of bond broken and bonds formed. So I have got more energy released in bond making here than is taken in when the bonds are broken. Perfect. Next. So it's now telling me to write an energy level diagram for that, and I've said that it's an exothermic reaction, so I have a negative delta H, I have a negative value for delta H, so I've labelled the overall energy change. You don't have to put the negative there, you just have to label it as the energy change, and I've labelled the activation energy, so it's just the same as the one we had before, isn't it? And the 3 marks again are for this time for making sure that line is lower, because I'm showing it's exothermic, and for labelling these 2 correctly. Okay, final question, question 4. So I've got another exothermic reaction, so I'm doing exactly the same as I've just done, and the marks are exactly the same. So again, it's exothermic, so the line should be lower. I'm labelling delta H and I'm labelling activation energy. So it's literally the same question twice. Sorry about that. So I've now got a final question, which is very similar, and I'm just doing a bond energy calculation again, and this time I'm just calculating the overall energy change again. So I'm just doing plus, minus, let's do the energy gained on this side on breaking the bonds. So therefore I've got 4 CH bonds, and I've got 1 carbon double bond, and I have 1 bromine bond, which overall is 2459. That's 1 mark. The next mark for my 1, 2, 3, 4 CH bonds, plus 1 carbon bond, plus 2 carbon bromine bonds, and altogether that is 2552, and then the difference between those 2 numbers is minus 93. So hopefully this is going to give you plenty of practice now of doing these calculations, and hopefully we're starting to get you're starting to get a bit of a way of laying it out yourself and getting a way of doing these. So the reaction is exothermic, and again, why in terms of bonds broken and bonds formed. So we've got more energy released when the bonds were made than taken in when the bonds are broken. I really slow down and write better, don't I, in case you want to have a pause and read this writing. should do that. I just want to get it through so you can get it done quickly. Okay, I hope that was helpful, and I will see you again next lesson.